So for this class, we're going to start with question 5 here. And in question 5, they're saying determine the force in members CD, CJ, KJ, and DJ. The first thing that you have to do is identify the members. CD is here. CJ is here. KJ is here. And DJ is here. So these are the members that they want us to understand or to describe. So they want us to find the forces which are inside these members and state if the members are in tension or compression. Then they're specifying that this is the method of sections. Now what I want to just highlight here is that even without this highlight there to say use the method of section, you have to know that if you are going for specific members of a truss system, then the best approach to use is the method of sections. You go for the method of joins when the question specifies use the method of joins, or when you actually want to know all the forces inside each member. Then the method of joins becomes better. Otherwise, it would be too involving to use the method of joins just to find what is happening at CD, CK, we don't even have CK, CD, KJ, DJ. Just for those four members to use the method of joins, it would be very difficult because most likely you start from somewhere here, then from there, or maybe you start from somewhere at A, find this member, then come to L, find this member, then go to B, find this member. See, it's taking you a lot just for you to come and find these four that you're looking for. So we take advantage of the method of sections when we want to just find highlighted members. So how does the method of section work? So depending on what you're trying to do, sometimes it's not necessary to understand the reaction forces, but in this case, to find what is happening, the section we can pick, it has to be such that it exposes the members we are targeting. In this case, we are targeting CD, CJ, KJ, and DJ. There is no right way of cutting through all the four members at once, so you can do it in 2 steps. In step 1, I'll get a section A, B here, so that I understand what is happening through CD, CJ, and KJ. Then after that, I'll come back to make another section that will help me understand what is happening through DJ. But for now, I'm going to find the first 3. But I see when I make my section, I need to choose now. Will I work with the section to my right, or will I work with the section to my left here? So which section do I want to use or to work with? I notice that regardless of the section I decide to pick, I have reaction forces that will be involved. If I pick the section to the left, I'll have reaction forces AX at that pin and AY. If I pick the section to my right here, I'll have one reaction force at G there that will be going upwards. So I'll say GY. So depending on which section I want to work with, I will need to find the reaction forces at those points. So in terms of choosing which section to use, it's completely up to you. Either side works here. But I will pick the section to my right here for one simple reason. To the right, notice that in terms of forces, I will only have to worry about the 5,000 there and the reaction at G. But if I pick the section to the left, I would have to worry about A in X, A in Y, the force at B, and the force at C. So it looks like I'll have too much to think about if I pick my section to the left. So I'll work with the section to the right. So if I work with the section to the right, I only have to worry about the reaction at G. So before I even go on with my section, I need to find the reaction at G. So free body diagram at G, we see to say we have a reaction that acts vertically upwards, that is GY. So We know to say we have reactions at point A as well. We're not really interested in what they are, so we can find them or we can choose not to find them, completely up to us. This is AY, this is AX. So if I just directly want to find the reaction at G, I would take moments about point A. So I'll take moments about point A equals to 0, since the system is in equilibrium. So how do we proceed here? About point A, it implies that AX and AY, the two forces pass through A, it implies that those two forces will not cause a rotation about point A. So I will only worry about the 400, 4,000, 8,000, and 5,000, including the GY. They are the only forces causing a rotation about point A. The 4,000 comes first. This is going to cause a clockwise rotation. So I am going to have 4,000. The distance, it has to be a horizontal distance from here to there, specified there. So clockwise minus. Next, I have the 8,000, also causing clockwise, so negative as well. The distance now will have to be 9 plus 9, which is 18. Then we have the 5,000 there, also causing clockwise about point A, but the distance will be 9 plus 9, 18, 18 plus 18, that is now 36. And then 36 plus 9, 45. Clockwise, so we have 5,000. Then the last one is GY. GY is now going the other way, so GY is causing anti-clockwise, so positive. And for GY, it's 45 plus 9, 54. So this is what we have for this part. So now we just have to solve this so that we find what GY is. Okay, so we're just going to make GY subject. Everything else goes to the right, becomes positive. So this is going to be positive 4,000 by 9, then positive 8,000 by 18, then positive 5,000 by 45, then all this will be divided by 54. So then we do the math to find what GY is. So what is going to be our answer here? What will be our answer here? Okay, so 7,500. So here the units are the pound. So let's say this is what we're getting as our GY. So since we now have our GY, we can go back to our diagram so that we figure out our section, since we now have the reaction we wanted. So with the reaction GY figured out, let's now go ahead and determine what we are looking for. So here we have our sections. So let's choose our section first. So here, remember our section, we're looking for CD, CJ, KJ, then DJ will be last. So we're going to cut through this part here. So what happens when we cut through that point? Well, now our members will be exposed. What was initially inside CD will now show as outside. So a force will show up there, but then it's going to be a sketch of the entire structure. But we are only interested in the outline. So there's no need for us to start putting these others here. No need for all those. Only the outline is okay. So just up to that point, and then we have this one here that tends to go towards C. So basically that is everything we need there in terms of the structure. Now let's indicate the forces. We start with the ones which are given from the get-go. We have GY here, and we found this one as 7,500. Then we have the applied force at point F here. So this is 5,000. Then we know this is point D. Just want to highlight that. This is point J. And then when they continue, this comes to point C. And then point D has been highlighted. Now, once we create our section, the forces inside the member, for example, DC here, will be exposed. Now, when they are exposed, here's what you need to keep in mind. In the method of section, when you create a section, if the force through the member is assumed to be coming out of the member that you have just sectioned, if the force through it is assumed to be coming out of the member like this, then the assumption is that the member is in compression. In the method of joint, this is in the method of sections. In the method of joints, however, when a force is assumed to be coming out of a joint or going away from the joint, then it implies that the assumption is that the member connecting to that joint is in tension. Here we are using the method of sections, and we have created our section. And we are going to assume that the forces through this section will be coming out of the section in this manner. Even here, we will assume the force will be coming out of the member in this manner. In the same way, even here, we will assume the force will be coming out of that joint, or not that joint, that member, in that way. But for calculation's sake, I'll keep in mind that these come to meet at C. So even here, these come to meet at C. Then here, of course, that passes to K, but not important. Now, let's include the labels. This force here is FCD. This one down here is FCJ. And then here, this is FJK. So now we need to do the math so that we can find those forces, the internal forces. So how do we do it? Well, it's really very straightforward. There are two methods you want to use. The whole structure before creating our section was in equilibrium. It means that even the section we have selected must also be in equilibrium. So if it is in equilibrium, it must satisfy the two conditions of equilibrium. Sum of moments about any point must be equals to 0. Sum of forces as well must also be equals to 0 for our structure. Now, it's easier to actually start with sum of moments because they avoid you having to start dealing with forces which are at an angle from the start. So here, we're going to start with sum of moments. But we want to be smart about our choices here. So we want to evaluate moments about a specific point that makes our work much more easier to do. So the first one that we're going to do, we can start with sum of moments about point J here. That is going to work. Or we can start with sum of moments about point C. So let's start with sum of moments about point C. You see, the best thing about this is that, you see, if moments are being evaluated at a given point, it then implies that any forces passing through that point will not cause a rotation about that point. Take FCJ for example. FCJ passes through C. FCD also passes through C. This implies that if I'm taking moments about C, it now means that those two forces will not cause a rotation about point C, meaning that only FJK, the 5000 there, and GY will cause a rotation about point C. So let's do that. So about point C, we're going to have FJC, JK I mean, times the distance. The line of action for FJK is horizontal, so the distance we are looking for has to be vertical. So that force times this perpendicular distance. So that is what we're going to use. So what is that perpendicular distance that we want there? So we go back to the original diagram. So it's from, where are we? Somewhere here. So from here up to here. That distance is given as 12 feet. So this is going to be times 12. Clockwise or anti-clockwise? The same scenario. Place a pen along the distance. Pin it at the point where the moments are being evaluated. Push that pen in the direction of the force. You'll see that this will be causing clockwise rotation. So clockwise, we take clockwise as negative. Next up, the 5000. The 5000 is vertical. The distance has to be from C up to the line of action of that force. What is this distance? We go back to the original diagram. It's from C. C is here up to the line of action of the 5000. So that is 9 plus 9 plus 9, 27. So we have times 27. Is it clockwise or anti-clockwise? About point C, you have to see that this will also be causing a clockwise rotation. So also negative. Next, the only one left, GY. GY going upwards to be the only one causing anti-clockwise. 7,500. The distance now, GY goes all the way up to the end. What's that distance? So that's from C, 1836 up to G. Equals to 0. See that here, clearly only FJK is missing, so take it to the right, rearrange, so that you're going to have FJK is equals to, this would be minus 5,000 by 27 plus 7,500 by 36 divided by 12. Okay. 11,250 pounds. So because this is coming out as a positive value, so it implies that the assumption that it was compression was correct. So keep it as compression. So having found one of them, we can go back. What else can we find? So now we know what FJK is. Let's get the others. So now we can come to the point J. Again, for J, we're going to take moments about J equals to 0. In the same way, we're picking J strategically because it makes our life easier. The force FCJ passes through J, meaning it does not cause any rotation about J. The force FJK also passes through JK, so it will not cause a rotation about JK. Notice that now the only forces that will cause a rotation about the point J, it's only FCD, the 5,000, and the 7,500. This will allow us to find FCD easily. So how are we going to do that? About J, only F, which one is it? FCD will cause a rotation. And notice that it will be causing an anti-clockwise rotation about J. So the distance will be from here to here. We did use it earlier. It's the same as 12. So it's going to be that times 12. Next, the 5,000. From J, the 5,000 passes through this. The distance we want is this distance here, from J up to point F. So let's go to the original diagram, but you should be able to remember that that has to be 18. But let's check the original diagram. From J is here, 9 plus 9. Yes, that is 18. So notice that the other one will have to be from J up to G. So this will end up being 27. So we saw that this one, 5,000 times 18. And for this one, clockwise or anti-clockwise, this one is causing clockwise about point J, so negative. Then you have GY. GY going upwards, so GY is causing anti-clockwise about point J. So because it is anti-clockwise, it will be positive. And GY is 7,500. The distance we saw that is 27, which is from here all the way up to the line of action for GY. So now we just have to solve this for FCD. Everything else goes to the right. This will be the positive one. This will now be negative. And then this will be divided by 12. Okay, so here we get this. So now that we have FCD, again, this came out positive.
It's giving me negative.
Yes, it's supposed to be negative. But you found the same answer, right? Just negative?
No.
Pardon?
Give me 9,375.
You got what?
9,000, negative 9,375.
375.
Let me try to repunch.
Okay, try to go through that. Let's see which one is correct. Nice. So here we're going to settle for this one. Okay. So the negative here just implies that our assumption that it was compression for this one, for the other one we saw it was correct, it was compression. But here it implies that this is not compression. Instead, when presenting it, we'll present it as a positive value, but we'll now say it is in tension. Now, we're not changing our diagram. So whenever we have to use the force FCD, we'll be using its negative value because we're not changing our diagram. But in presenting, we're just presenting it like this and then just stating tension. We will not use this value. If you want to use this value, it means that you have to change the orientation on the diagram as well, which we are not going to do. Okay, so we have found FCD as well. Now we move on to the last one for this one, CJ. So how do we figure out CJ? For CJ, we see that we can use rotations, but it might be a little bit too much for us. So instead, we decide to first break CJ into its components. So we first want to break CJ into its components. So how do we do that? So we can get our structure again. But now want to represent CJ into its bits and bits, into its component. So we know CJ is acting in this direction, from J to C. But what do we know? We know that the distance from this level, the horizontal level, all the way up to where J is, up to where C is, this distance, we saw this was 12. And the distance from here up to J, we saw this distance was a 9. So this is 9 here. And the vertical part is a 12. We can actually verify that from the diagram, which is here. The distance from J, we're looking for this one, the one that runs to this. The distance from J to K, that's a 9, and the distance from K to C, that's a 12. So that part has checked out. Now from there, we can easily get the angle that we're going to use here to express CJ in component form. So we know to say by tan opposite over adjacent, so that theta is equals to tan inverse of 12 over 9. So here we're getting 53.13 degrees. And now that we have the angle, we can easily break CJ into bits and bits. Because if this is 53.13 degrees, and this is FCJ, we can easily say that the horizontal part of it is going to be FCJ, and then cos 53.13. The vertical part is going to be FCJ, then sine 53.13. Now, what does this imply? It now implies that where we have FCJ, we can actually remove FCJ. And in place of FCJ, we can look at it in terms of its components. This is FCJ, then cos 53. And then this is FCJ, then sine. I have to see that these forces are the same. I can say they're acting here, I can say they're acting here, I can say they're acting, I can even say they're acting right at J there. Because as long as there is no force along the length CJ, they can act at any point. When you're using the method of, if you're using the sum of moments, that becomes very important. But if you're using sum of forces, it's okay, regardless, even if you don't understand that concept. So here I'll use the sum of forces since everything else is now known. We already know FCD and FJK. So I'll easily just take sum of forces now. I can take sum of forces in the Y or in the X, either will work. Let's take in the Y. If we sum forces in the Y, we have the 5,000 going down. We have GY going up. Then we have CJ going up. I think that's the last one, so equals to 0. So this means that FCJ is equals to positive 5,000 minus, okay, the 5,000 becomes positive to the right, the 7 becomes negative. So that in the end, so what becomes our answer here? Negative 3,125, like this.
Yes.
Okay. Again, because this has come out as a negative, we can conclude that this is supposed to be 3,125. The assumption was compression, so the actual must be tension. So this is what we are finding here. So we have covered 3 of the members they wanted. Only one is left. Which one? Let's go back to our diagram. We have sorted out this one, and this one. Only this one is left, DJ. Now for DJ, I will show you a trick. Let me start with what I want you to do later on. Later on, I want you to pick a section. You can even pick this section here. Just break it through this part here. Notice that then it will mean that you have this, you have this with point D being here, then you have this one here. It's actually very straightforward if you think about it. You have a force going through this. This is going to be FDC or CD. We got it as CD earlier on. It doesn't matter. And then you have this one here. This is going to be FDE. And then here, you're going to have FDJ, which is what we are looking for. But for this one, you have to see one thing. When you sum forces in the x-axis and equate to 0, notice that FDE minus FDC must be equals to 0. Clearly, FDE will have to be equals to FDC. But when you sum forces in the y-axis, observe that CDJ is alone there. So FDJ must be equals to 0 since it is alone. Here, we quickly see that FDJ is a zero force member. That becomes an obvious conclusion there. It's one thing that you have to look out for every time. Here, FDJ is a zero force member. The funny thing is, there we have seen mathematically to say that it comes out as a zero force member. But what I want you to observe is that if you have a member like this here, and then somewhere here, a member is connected. You have to observe that even in this case, as long as this is part of a truss, I'm saying this is part of a truss here. Even in this case, the force that goes through this member, you have to see that it will actually end up being 0. As long as you only have 3 connections at that point, and as long as you don't have an additional force exerted there, then you expect that this force here is going to be a zero force member. Look out for such. Again, you can have a scenario where this is part of a truss system, and then you have maybe a third one in this manner. Again, the emphasis is as long as there is no external force exerted at this joint here. As long as this is what you have to see that firstly, this one here, even if they're not the same, the key thing, most likely they would not most likely, they will be the same. This one and this one will be the same. And the one that acts along this member will be a zero force member. This is going to be a zero. Why, you might be wondering? It's very simple. If the angle here is a theta, you have to see that this force will have two components. The vertical component will be given by whatever, let's say this is F1, this is F2, this is F3. F3 is going to be F3 sine here in the y-axis, sine theta, and then in the x is going to be F3 cos theta. But my emphasis is in the y-axis. Notice that it will still remain the only one in the y-axis. F1 is strictly in the x, F2 is strictly in the x, meaning F3 will be the only one with a y component. So as long as there is no external force being applied here, when summing forces in the x-axis, in the y, you still have this is equals to 0, meaning that F3 will still be equals to 0. It will still be a zero force member. So you want to look out for such tricks. They might simplify your life when dealing with some of these. So here, even without solving the problem, I was able to conclude that the force through dj is 0. dj is a zero force member. Even here, can you identify a zero force member for this structure? Can you identify it? Anyone?
Is it CG?
CG, yes. CG is a zero force member based on this part here. This and this will be equal. This will be a zero force member.